How is this possible? At a distance of 11 billion miles from the Sun, the venerable Voyager 1 spacecraft, operated by NASA, crossed the border between the solar influence and the interstellar medium on August 25, 2012. The primary mission of Voyager 1 and 2 was to study Saturn and Jupiter. The first Voyager set out on a different course to the solar system's periphery since it was more focused on Saturn's enormous moon Titan, while the second Voyager also visited Neptune and Uranus. Voyager 2's 1989 flyby of Neptune was the catalyst for the creation of the Voyager interstellar mission. Voyager 1, along with its twin, is currently conducting groundbreaking research, still running strong and sending back data. Now, researchers are receiving concerning responses that reach the Milky Way's protected regions. What is happening to one of the most recognizable space exploration objects ever made? Was that an unfounded alarm? Join us as we explore how Voyager 1 suddenly received an alarming response from a nearby object in space. As Earth's first emissaries to the outer planets, the Voyager spacecraft captivated the world in the 1970s and 1980s by offering up-close views of Neptune, Saturn, Jupiter, and Uranus. On August 17, 1977, Voyager 2 was the first to blast off into space, and on September 5, a few weeks later, Voyager 1 did the same. The Voyager twins serve as living monuments to their time in many respects. Their data transmission speeds are around 40,000 times slower than 5G internet. They both have 3 million times less memory than modern cell phones, and they both have an 8-track tape player for data recording. They both have a golden record, a message from humanity to the cosmos with greetings in 55 languages, images of Earth and its inhabitants, and music spanning from Beethoven to Chuck Berry's Johnny B. Good. Although the missions have received little media attention in the last several decades, project scientist Ed Stone has overseen the continuous exploration of the solar system by the tiny spacecraft. Rankin was chosen to serve as the Voyager deputy project scientist, and Linda Spilker, who has been affiliated with the mission since 1977, assumed Stone's role following his retirement. As the sole instruments to ever traverse interstellar space, the Voyagers continue to push the frontiers of space exploration despite their now antiquated memory and transmission systems. The planetary encounters that have made Voyager famous began 2 years after its launch in 1977 when the twin probes passed by Jupiter. Voyager 1 and 2 both visited Jupiter and Saturn before splitting ways. Voyager 2 continued on to Uranus and Neptune at a slightly slower rate. Though the Voyagers wouldn't really enter interstellar space until they left the heliosphere, the space bubble surrounding our Sun, the Voyager interstellar mission formally began on January 1, 1990, and all planetary encounters were completed within a decade. In August 2012, Voyager 1 reached the heliopause, marking 2 peaceful decades since it left the outer planets behind. 6 years later, in November 2018, its slower twin breached that boundary. The Sun is a nuclear explosion that releases high-energy particles all the time. These particles are hurtling through our solar system at breakneck speeds, causing the Sun's influence to radiate far beyond the planets and eventually collide with interstellar particles. The termination shock is the inner, roughly spherical barrier. The heliosheath is located beyond it. As Voyager 1 sped past the heliosheath, the solar system's most distant neighborhood, and what is believed to be the heliopause, its actual boundary, scientists had anticipated that it would pick up on 2 distinct signals. Thankfully, Voyager 1's and Voyager 2's critical instruments were operational even after all this time, and the spacecraft's nuclear power supply kept it going. For some reason, scientists could only confirm the occurrence of one of 2 occurrences. According to scientific predictions, Voyager 1 would no longer detect the solar wind, a stream of charged particles emitted by the Sun, when it fades away near the border between the solar system and interstellar space. Yes, that did occur. Additionally, they anticipated that as Voyager 1 departed the magnetic bubbles surrounding the Sun, the field's direction would alter. That failed. The natural world has much greater imagination than humans. The spacecraft saw a brief decrease in the strength of the solar wind. It weighs around 1,600 pounds and, according to NASA, could fit inside a cube that is 13 feet on each side. Excitement was the word that Edward C. Stone used to describe it. Such a precipitous decline was unprecedented. It was completed in just 24 hours. It was back up and running 5 days after that. During the middle of August, there was a brief and deeper decline. Next, on August 25, the solar wind decreased by a factor of over 1,000, eventually disappearing to levels that couldn't be detected. Concurrently, there was a 99.3% increase in the amount of extrasolar cosmic rays. We appeared to be outdoors. However, the field's consistent and unwavering orientation suggested that Voyager 1 remained ensnared in the Sun's magnetic field. Here, solar particles may be able to escape because the solar system's magnetic fields partially merge with those of the interstellar medium. According to scientists' best guesses, the Voyager spacecraft has definitively left the heliosphere and entered interstellar space due to the high particle density there. The heliosphere is home to the solar wind, a stream of charged particles emanating from the Sun. At those distances, the density was 10 times higher than what we observed in the solar wind. The identical increase in particle density was observed by Voyager 2's detectors upon entry into interstellar space on November 5, 2018. Though the probe's entry into interstellar space was unambiguous, the heliopause, a twilight zone separating the heliosphere's bubble-like interior from interstellar space, exhibited peculiarities that were not anticipated. During their 2-month journey, each spacecraft transmitted data on plasma density peaks and valleys. We were expecting a beep, but the heliopause was deeper and more complicated than we had imagined. It's not like a line or a door. However, it also serves as a barrier that facilitates dialogue. Data on magnetic fields collected by Voyager 1 in 2012 and Voyager 2 in 2016 led to the astounding revelation that particles enter and exit the heliosphere. Scientists were perplexed by the data on heliopause magnetic fields collected by the Voyagers since theorists predicted that the galactic magnetic field would be inclined to the solar magnetic field. A change should have occurred at the point where the solar magnetic field and the intergalactic magnetic field met. Voyager 1 and 2 did not pick up on changes in the direction of the magnetic field. Though there was no shift in angle as Voyager crossed, in the absence of spinning, the magnetic field maintained an almost solar-like shape. It remains a mystery. It's as if the heliosphere has these thoroughfares that particles can use to enter and exit. It's likely to be an area where the magnetic field re-establishes itself. The heliopause seems to be the distorted heliosphere surface that reacts to solar activity, although for what reason is still unknown. The amount of incoming radiation was nearly 10 times more outside the heliosphere than inside the bubble, according to Voyager's measurements. The Voyager spacecraft demonstrated that the Sun is absorbing up to 90% of the interstellar radiation through its heliosphere and solar wind, which means that astronauts are not directly exposed to this potentially lethal radiation. In reality, the solar wind is shielding us from harm. Nobody understood how heavily insulated we were until the Voyagers arrived. Another unexpected finding from the Voyagers was the Sun's boundary interaction. Like two north-north magnets, magnetized plasmas cannot mix when they come into contact with one another. This means that solar wind or solar plasma cannot mix with interstellar plasma. However, there are also non-electrified particles in the universe that could care less. These particles would just ignore the heliospheric borders and continue on their way. Both of these things eventually impact our solar environment, and our environment can do the same for them. Other missions, including IBEX and New Horizons, have offered supplementary information regarding the characteristics of these distinct interactions in the heliosphere, which the Voyagers cannot directly measure. To supplement the deep but geographically limited data acquired by the two Voyagers, IMAP will launch in 2025 and provide a detailed map of that elusive boundary zone. Now that Voyager 1 has traveled $40 beyond the heliopause, researchers can finally learn the truth about the nature of the interstellar medium. It is discovered to be far more affected by the heliosphere than initially believed. The Voyager probes have shown that the interstellar medium is not calm but rather disturbed and affected by solar winds. We still have no idea what's happening, and it's completely different from what we anticipated. According to the results, galactic cosmic rays don't act the same when oriented either parallel or perpendicular to the solar magnetic field. Solar coronal mass ejections, which disrupt the Sun's magnetic field and extend into the interstellar medium, are a possible explanation for the data. The new way cosmic rays can reach Earth has scientists scratching their heads. At the same moment, astronomers uncovered a creepy and weird phenomenon happening on the solar system's periphery. The heliopause and interstellar medium seem to be rippling and producing oblique angles in an unforeseen way. Although the idea that the heliopause can and does change shape is not new, scientists have just recently established that this is the case. This finding was derived from information gathered by NASA's Interstellar Boundary Explorer satellite, which studies the emissions of energetic neutral atoms produced by the interaction of solar winds and the interstellar medium, and data collected by Voyager 1 and Voyager 2, the only spacecraft to have left the heliosphere so far. So far, the sole direct measurement of these borders locations has come from the Voyager spacecraft, but that was at a single instant in time and space. Based on the data, scientists have developed models to foretell future heliopause shifts. A constantly shifting border is formed by the mutual pulling and pushing of solar winds and the interstellar medium. However, new information on the heliopause has come to light, which runs counter to what was previously known. During a few months in 2014, IBEX recorded the illumination of ENAs, which pointed to heliopause asymmetries. The researchers later discovered that these asymmetries did not match predictions. In addition, scientists found that the heliopause shifted considerably in a relatively short time span when they reviewed data from the Voyager 1 and Voyager 2 missions. This sheds light on the reason for the significant time difference between the two probes' 2012 and 2018 entries into interstellar space, respectively. However, models also fail to account for that type of heliopause movement. The researchers characterized these differences as intriguing and potentially controversial. They intend to pursue further heliopause research in hopes of gaining further understanding with the launch of NASA's Interstellar Mapping and Acceleration Probe in 2025, an upgraded satellite capable of detecting energetic neutral atoms. Until then, all we can do is speculate about this spooky solar system event. Plutonium-238, with an 88-year half-life, powers the Voyagers. At launch, it seemed like an eternity, but now we're almost halfway through the half-life, and the spacecraft's operating power is running low. With the completion of the planetary mission, the Voyager teams disabled several devices, including the cameras. It was either switch off more instruments, turn off the heaters, or lose the spacecraft. No one knew if the instruments could work without the heaters. Thankfully, even after the heaters were turned off one by one, the equipment kept on generating and sending data. Older spacecraft also lacked the transmission capacity necessary to send a strong signal back to Earth over billions of miles, so telescopes on Earth have had to work harder and harder to pick up their weak signals. Ed likened it to a space-based refrigerator light bulb that blinks. We are referring to that level of signal intensity. Therefore, we must make tremendous efforts to communicate with the Voyagers as they continue to recede into space. We were able to maintain communication with them because of technological developments on Earth, such as the construction of 230-foot dishes for the Deep Space Network. It is a tribute to the genius of the Voyager's engineers that the spacecraft continues its mission to fearlessly travel where no spacecraft has gone before. Traveling at a velocity of approximately 1 million miles per day, Voyager 1 has already departed the heliopause by billions of miles, a distance equivalent to that of Neptune from Earth, and it continues to make astounding discoveries. It is still subject to the sun's rays even at that distance. As solar flares and coronal mass ejections make their way through the solar system, they can accumulate and combine into massive events that push against the heliopause, causing ripples to ripple across interstellar space. Voyager is able to note it. Because of their great distance from Earth, the Voyagers also see the Sun and Earth from an entirely new angle. Voyager gives us a first-of-its-kind opportunity to observe our star and solar system from an alien perspective. For decades, scientists have studied other stars and collected remote data, but our knowledge of our own star has been limited to what we have observed from the inside. The question then becomes, how do others perceive us? A spacecraft in orbit, or even better, two spacecraft in different parts of the galaxy, would be the only sure method to find out. According to NASA, a computer fault has caused a temporary communication breakdown between the 46-year-old Voyager 1 spacecraft and its mission team on Earth. As the weathered spacecraft travels over unexplored cosmic terrain towards the solar system's periphery, engineers are frantically attempting to find a solution. Among Voyager 1's three processes is a flight data system that compiles readings from the spacecraft's scientific instruments with engineering data that represents the vessel's present health status. That data is sent to mission control on Earth in binary code, which is a string of ones and zeros. It seems like the Voyager 1 flight data system is presently in a loop, like something out of Groundhog Day. When the telecom unit of the flight data system started transmitting a backup pattern of ones and zeros as if it was stuck in a loop, the mission team initially recognized the problem late last year. Due to an issue with the communications unit, Voyager 1 is unable to communicate any scientific or engineering data back to Earth. While the spacecraft may still receive and execute orders sent by the mission team, there has been no useful data returned from Voyager 1 since. The researchers issued commands over the weekend to restart the flight data system. Engineers are currently attempting to gather more information regarding the root cause of the issue before deciding how to fix it. Weeks may pass during the process. It does not appear that the present problem is related to other issues that Voyager 1 has had in the past few years. The previous occurrence of a comparable, but not identical, fault with the flight data system occurred in 1981. Both Voyager probes are undergoing additional trials, and the mission team is left with nothing but the original instructions written decades ago, which don't cover the problems the spacecraft are having as they age. In order to avoid any unanticipated consequences, the Voyager crew is waiting to issue further directives to the ship until they have thoroughly examined all possible ramifications. Because of how far away Voyager 1 is, Earth-sent commands take 22.5 hours to reach the spacecraft. On top of that, they have to wait 45 hours to hear back. To prolong the missions of the aging twin Voyager probes and conserve power, the team has been gradually turning off instruments. As stated before by Voyager's project manager Suzanne Dodd, Voyager 2 lost contact with Earth for 7 months in 2020, among other unforeseen problems and dropouts experienced by both spacecraft. When a command accidentally turned Voyager 2's antenna in the wrong way last August, the mission team resorted to a last-ditch shout method to get in touch with the spacecraft. The primary benefit of the mission is its length. Even if the crew is aiming to resume Voyager 1's regular data transmissions, extending the probe's flight distance from the heliosphere allows scientists to observe changes in particles and magnetic fields, for instance. However, data from Voyager 1 will be missing from that data set unless the spacecraft can communicate with Earth in the future. In order to keep both spacecraft powered up and continue their record-breaking missions, the mission team has been getting inventive with its techniques. In recent years, the Voyagers have continued to operate for an unprecedented amount of time, far beyond the end of their primary missions. Therefore, we anticipate that problems will emerge, even though the engineering staff is working tirelessly to ensure their survival. So, where do the Voyagers go from here? As they enter the clean interstellar medium, the silent ambassadors will gradually become silent. As solar activity decreases and atmospheric turbulence decreases, the spacecraft will most likely collect interstellar materials. Mission personnel have stated that the two spacecraft are nearing the end of their operational lifespan due to running out of power. The last time scientists hear from them is likely to be in the 2030s at the earliest,